290 million years after the Big Bang, a galaxy is glowing where nothing that big has any right to be. It is 1,600 light-years across, weighing as much as hundreds of millions of suns. Astronomer Ivo Labbe described the discovery as the cosmic equivalent of meeting a toddler who weighs 100 kilograms. The metaphor stuck because the math did. Galaxies this mature should take billions of years to assemble. This anomaly directly challenges Lambda-CDM, the standard model that governs our understanding of the universe's 13.8 billion-year evolution. This framework requires a slow, rhythmic progression of gravity and time. According to the model, the first few 100 million years were a hot fog of hydrogen and helium. The first stars were supposed to switch on near the 200 million-year mark. These early galaxies were expected to be faint, ragged smudges, cosmic embryos. They needed time to grow into anything substantial. Hubble's deep field observations mostly confirmed this, but the James Webb Space Telescope changed the input. Since opening its golden mirror, it has been pulling objects out of the deep infrared sky that the standard model never predicted: massive, dusty, and impossibly mature. Follow-up observations from the ALMA radio array detected oxygen in these early systems, at 10 times the abundance theory expected. Since oxygen is only forged inside stars that have already lived and died, its presence proves that entire dynasties of stars had already burned out before this light was even emitted. The problem extends to the physical mechanics of how a galaxy builds itself. Cosmic growth is restricted by a structural ceiling that every galaxy must obey. This is a dark matter halo. In modern cosmology, these invisible structures form first, acting as gravitational anchors that catch and pull the normal matter needed to build stars. The size of the halo sets an absolute ceiling. You cannot have more stars than the available mass inside the halo allows. It is the physical limit of how much matter can collapse into starlight within a given volume. This ceiling is the foundational load-bearing beam of the standard model. It is how we explain the cosmic microwave background and the large-scale web of galaxies we see today. Now, Webb has identified the red monsters, 3 enormous galaxies in the universe's first billion years, shrouded in dust with stellar masses that rival the modern Milky Way. To understand their efficiency, look at a modern massive galaxy. They typically turn about 20% of their available gas into stars. Most of the gas remains scattered or is blown away by supernova feedback. The red monsters are running at twice that rate. They are converting half of every available baryon into starlight, pressing against the limit of what physics allows. When cosmologists count the number of these massive galaxies and compare them to the number of dark matter halos that should exist that early in time, the numbers do not line up. There may not be enough massive halos in the early universe to hold all the stars Webb is seeing. The data suggests the containers are smaller than the contents they are supposed to hold. This leaves 2 options. Either the standard model is broken, or we are misinterpreting the early universe's conditions. Most researchers are currently looking for adjustments that could absorb this data. One fix is the recipe for star formation. A few giant, ultra-bright stars produce the same light using less mass, shrinking our weight estimates. Another is burst mode formation. In the denser early cosmos, the first stars triggered furious chain reactions, forcing rapid stellar collapse. More exotic ideas like early dark energy or modified gravity are waiting in the wings, but they haven't won the day yet. They remain possibilities if the simpler adjustments fail to bridge the gap. The standard model has dents, but not cracks. The thrill of this moment is that the universe has handed us a sharp, undeniable mystery, sitting in real data, daring us to look again at the first chapter of cosmic history. Galileo's early lens broke the Aristotelian sky, and Hubble's wide field proved the Milky Way was not the whole show. Webb is now bending the story of how galaxies first lit up the dark. We are not running out of universe to discover. We are just beginning to listen on the right frequency. The massive toddler galaxies are still out there, glowing, ancient, and waiting for the